when both variables are non-numeric and categorical. When both variables are non-numeric and categorical. Till now we have done with one numeric and one categorical. In this case, both variables are non-numeric and categorical. We have to use chi-square test of independence. When both the variables are non-numeric and categorical, we have to use chi-square test of independence. The input of this test is cross tabulation. The input of this test is cross tabulation. The null hypothesis for this test is there is no association between both variables. Alternate same statement, remove the word no. There is association between both variables. There is association between both variables. Null is no association. Alternate is association. Same p-value based interpretation. So, test null no association between season and weather situation. Test null, no association between season and weather situation. PD dot crosstab bicycle data dot season comma bicycle data dot weather situation. This is a cross tabulation. All right. Now the function is chi2 underscore contingency. SciPy dot stats chi2 underscore contingency, which is the function for chi-square test of independence. SciPy dot stats chi2 underscore contingency. Now it returns the output includes chi-square statistic, the formula statistic, the p-value, the degrees of freedom, and expected table. So what happens in chi-square test is from the actual table, we calculate an expected table. From the actual table, we calculate an expected table. The formula is row total multiplied by column total divided by grand total. Using that, we will calculate a expected table from this table. And the formula is sigma observed minus expected whole square divided by expected. So I will show you the calculation in Excel, then you will understand. But the output includes the test statistic or the formulated statistic. The includes p-value, degrees of freedom, and the expected table. From scipy.stats, import chi2 underscore contingency. Chi2 underscore contingency, in brackets, I'll copy the crosstab thing. So the p value is this. We reject the alpha. That means there is a relationship between season and weather situation. Degrees of freedom is number of rows minus 1 multiplied by number of columns minus 1. Yes. So degrees of freedom is generally required for you to, when you're using table, you require it. Otherwise, you don't need to require. You don't need it. This is the formula. Observed minus expected whole square divided by expected. For expected table, this is the formula. Row sum into column sum divided by grand total. So in day Excel sheet, we have already created a pivot table. Go to the pivot table in the day Excel sheet, the pivot table sheet. We'll drag season to rows, drag weather situation to columns, drag any one of them to values, count. So this is a cross tabulation which I have created in Excel using pivot table. Using the pivot table, I have dragged season onto the rows. I have dragged weather situation onto columns. I have dragged any one of them to values and changed it to count. The pivot table season to rows, weather situation to columns, any one of them to values, you'll get the values. Got it? Day Excel sheet, pivot table. Season to rows, weather situation to columns. Any one of them to values. Any one of them you can drag to values second time. Any one of them you can drag second time to values. Which one? Got it, all of you? So copy the table into a new sheet. When you paste it, paste special values and number formatting. Copy the table into new sheet. When you paste it, paste special values and number formatting. Copy the table, paste it into a new sheet. Now you have to create a dummy table exactly one row below. So this is our observed table. From this, we are creating an expected table. The formula for expected table is for each cell, row total multiplied by column total, row total multiplied by column total divided by grand total. Row total multiplied by column total divided by grand total. So if you look at the table which I gave here, this is row total. This is column total. And this is your grand total or total number of observations. So row total, column total, and grand total. So this is your row total, this is your column total, this is your grand total. All right. Now in the first cell is equal to open bracket row total multiplied by column total close bracket divided by grand total. Now I am going to drag the formula vertically. If I am dragging the formula vertically, the column total will be fixed. The column total will be same. Row total will change. Column total remains same. So I'll fix the column total by pressing Fn plus F4. And grand total is also same for all the cells. That also I'll press Fn plus F4. I'm going to drag the formula vertically. Is equal to open bracket row total multiplied by column total divided by grand total. Column total is fixed. It is common for, because I am drawing the formula vertically, it is fixed for all the vertical cells. Similarly, grand total is common or fixed for all the vertical cells. So I am putting Fn plus F4, absolute cell referencing. Now I got 114.68. Now I will drag this formula down. Right? Same thing I will apply here. Is equal to open bracket row total multiplied by column total will change here. Column total will change. Row total remains the same. So I will press Fn F4 for column total divided by grand total. Grand total remains same, Fn and F4. I will drag this formula down. Similarly, is equal to open bracket row total multiplied by column total will change Fn plus F4 divided by grand total, which again remains constant, Fn plus F4. So I will drag it down. Now, if I go to Python, I would have got the same values in the, see here, 114.64, 61.15, 5.19. See these metrics which are there here, they exactly match with this metrics. Now, I will show you the formulas. Don't worry. Let me just complete. So, for calculating the chi-square, you have to use the complex formula. Now, the chi-statistic is equal to open bracket observed minus expected to the power of 2 divided by expected plus open bracket observed minus expected to the power of 2 divided by expected plus open bracket observed minus expected to the power of 2 divided by expected plus open bracket observed minus expected to the power of 2 divided by expected plus open bracket observed minus expected to the power of 2 divided by expected plus observed minus expected to the power of 2 divided by expected plus open bracket observed minus expected to the power of 2 divided by expected plus open bracket observed minus expected to the power of 2 divided by expected plus open bracket observed minus expected to the power of 2 divided by expected plus observed minus expected to the power of 2 divided by expected plus observed minus expected to the power of 2 divided by expected plus observed minus expected to the power of 2 divided by expected. 14.88. If you go to Python, you will also get the same value. See 14.883876. So you can see here, right? The output 14.88386. So it uses this formula, but you don't need to worry. We can directly calculate the p-value. There is simply all we need is p-value, right? So p-value, it's very easy to calculate. Is equal to chi-square dot test actual range comma expected range to get the p-value. Same p-value 0.02 what you got in Python. See 0.21179. So this is the methodology. I show you the chi-statistic calculation, which is a little bit complex, but this is the formula which we use. Row total divided by column total multiplied by grand total. Just look at the formula. We are dragging the formula vertically, so we are fixing the column total. If you are dragging the formula horizontally, we will fix the row total. Okay, so you can do the calculation. Follow the color coding. You have to calculate this. This is mandatory. Once you have done this, you can directly go for p-value. No, this is not required. See, what happens is, one of the frequent question we are asked you is chi-square test, because most of the time in industry data will be text. Yesterday, one of the PGA 18 student called up, working in Capgemini. He got some data related to online betting and casino data. There, all the columns except the bet amount is categorical. Only one numeric variable is there, amount betted. Rest of all are categorical. So he was, and then there are a lot of missing values in categorical data. So he was asking, what should I do with this categorical data missing values? And some of the missing values are almost 60 to 70% of the column. But client is insisting on filling the missing values. So I told him use the algorithm. Python will not work. Use R and use the mice algorithm to fill it up. Since 8 lakh rows are there, it will take 2 hours. So most of the time when you see real-time data, it will be categorical in nature. 60 to 70% of the data will be text or categories. So chi-square test is one of the most used tests in industry. Chi-square test is one of the most used. So you need to have understanding of the formula. What is the formula they will ask you? What is the formula for calculating the expected test? They will ask you. And they will ask you the formula for degrees of freedom. Rows into one, rows minus 1 into columns minus 1. So this is one of the most common interview question we see in data science. Chi-square test of independence. The null is no association between both variables. Alternate is there is association between both variables. For expected table, row total multiplied with column total divided by grand total. Observed minus expected whole square divided by expected for each cell. For each cell, observed minus expected whole square divided by expected. Observed minus expected for every cell, corresponding cell. Got it? Anybody has doubts? Problem, error? Chi-square dot test is equal to type CHASQ. It will automatically suggest is equal to dot test actual range and expected range. Don't select the headers and totals. Hello. Yeah, hello. Calling from? Yes, yes. Okay. Yeah, yeah. 12 months. 12 months. 50004 is 834. 44. 1978. Yeah. Yeah. Ah. Yeah, okay. 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 Yes. Yes. All right. Yeah. Yes. Good morning. Yes. Hmm. Yes. 1 second. Let me check. No, I have not received. Received 1597. Okay. Do this. Yeah. Do this. Weekday and working day. PD dot cross tab bicycle data dot working day, comma, bicycle data dot weekday. Cross tabulations. Chi2 underscore contingency, PD dot cross tab. Reject null. All right, done. Contingency expected. All right, done. Now, one other important test which we do is paired sample t-test or related sample t-test. Here, the data will be in form of before and after an event. Data comes from single entity but at 2 time intervals. The blood pressure of the patient before taking the tablet, blood pressure of the same patient after taking the tablet, before and after. For paid sample t-test, single entity will give you data at 2 time intervals, before and after. Blood pressure of the patient before taking the tablet, blood pressure of the same patient after taking the tablet. So before and after, this is one of the most important t-tests in industry, particularly when you are looking at advertising and what you call marketing communications. Sales before advertising, sales after advertising. Sales before social media campaign, sales after social media campaign. Leads generated before Facebook campaign, leads generated after Facebook campaign. So before and after is one of the wide used tests to understand the efficacy of the strategy which you have implemented in marketing or finance or any other part of your organization, predominantly used in sales and marketing, to compare sales before and after a campaign, to understand whether the campaign was successful or not. How will we know? If the sales increases after doing an advertising campaign, we can say that the sales campaign was successful. If the sales did not increase as expected, we can say it has failed. The null hypothesis is there is no significant difference in average variable before and after event. So alternate is there is significant difference before and after the event. Test null, the average CPI inflation, consumer price inflation before and after demonetization equal. So test null, the average inflation before and after demonetization is equal. We'll take 12 months before and 12 months after, and then we will do the test. November 2016 is when the demonetization occurred. So before demon, what was the monthly inflation? 3.35, 4.14, 5.30, 6.46, 6.13, 6.59, 5.86, 5.51, 5.53, 5.91,
Even this taking mean
yeah, 6.32, 6.72. After demon is equal to 2.59, 2.23, 1.86, 2.62, 2.61, 2.21, 1.09, 1.08, 1.79, 2.52, 2.89, 3.24. Just a second. Paid sample t-test. There is a formula. 1 second, let me just copy the formula and then you can look at it. Mark down. So this is the formula, sigma d by n into sigma d square minus sigma d whole square divided by n minus 1. D is the difference between before and after for each value. Right? From scipy dot stats, import t-test underscore rel, t-test underscore related, t-test underscore related, before demon, comma, after demon. So in t-test underscore related, calculate a t-test on the two related samples. The two related or repeated samples have identical averages. Related or repeated samples have identical average. Related, t-test underscore rel. So it gives you the t statistic and the p value. See, t statistic and the p value. So since p value is less than 0.05, we reject null. That means there is a relationship between demonetization and inflation. there is a relationship between demonetization and inflation. So demonetization has affected the inflation. Done? Test null, the average CPI before and after GST implementation. Before and after the GST implementation is equal. Now GST was implemented in July 2017. Before GST, what was our monthly inflation? 1.08, 1.09, 2.21, 2.61, 2.62, 1.86, 2.23, 2.59, 3.35, 4.14, 5.30. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, one more. 6.46. After GST implementation, the values are 1.79, 2.52, 2.89, 3.24, 3.97, 4.00, 5.11, 4.74, 4.36, 3.97, 3.96, 3.93. So the mean before GST is 2.96, mean after GST is 3.70. T-test underscore L before GST, comma after GST. That means there is no, we fail to reject the null. Is greater than 0.05, we fail to reject null. So GST did not affect the inflation. GST did not affect the inflation. GST implementation has no effect on inflation. Fail to reject means no effect. Reject means effect. Got it? Done, all of you? Now, all of you go to your bank data set thing which you worked upon earlier. Bank data set you have worked on, right? And you submitted. Open that notebook. Run all the cells. Do these tests on the same bank sharing data notebook. Run all the cells. Run all the cells. Open the notebook, run all the cells, and do this hypothesis test. So when you have the real-time data, it will be like this. You will have month and this. You have to use an if statement and then you have to input this before and after.
Define for this we do define mean and all when you do that. Because before I know what it's like analysis of variance. So that's why I can understand define mean for it.
X minus mean. What is the formula of ANOVA? Look at the formulas of ANOVA. X minus mean whole square, mean minus grand mean whole square. Everything is mean only, right? X bar is mean. Mean minus grand mean. So see, hypothesis testing is all about mean comparison. Comparison of means of groups. Only t-test, because there are two types of tests, assuming equal and unequal variances, we have to check variance, but it is not a criteria to be checked. And in real time, you will not see equality of variance. It only happens only with certain types of economic data. It does not happen in business data.
So you said that if median you by outliers when we consider median, in that case, you will expect
What is the relevant of skewness here? Is skewness relevant here? Then what is the point of using a test for hypothesis? When it is not relevant here, why do you need to do a hypothesis test? In hypothesis test, the only relevant metric is mean, not any other metric. Is that clear? Only thing in hypothesis testing is mean. Nothing else. Done? Okay. So we have been trying to understand the relationship between numeric and categorical or categorical variables. Now, within EDA, there is one more thing called bivariate statistics, which gives you the measures of relationship when both variables are numeric. When both variables are numeric, we have these bivariate statistics, which are the relationship measures. There are two measures. One is covariance, points to the directionality of movement of two variables. It simply points to the directionality of movement. Positive covariance. Both variables moving in same direction. Negative covariance. Both variables moving in opposite direction. So when you look at covariance, you only look at the mathematical sign. You don't consider the value, you only look for the mathematical sign. Mathematical sign. Look at the mathematical sign. If it is negative, the variables are moving in opposite direction. If variables are moving in opposite direction, no relationship. Both of them are moving in same direction, positive covariance, they are related to one another. Same direction, related. Opposite directions, no related. So in covariance, you will just look for the mathematical sign. Now the second and the other most important is correlation. Quantifies the relationship quantifies the relationship in numeric terms. Correlation gives a numerical value to the relationship. Quantifies the relationship in numeric terms. Correlation lies between -1 to 1. Correlation lies between -1 to 1. Now, the correlation values so these are the values. -1 to -0.7, strong negative. -0.7 to -0.3, moderate negative. -0.12 plus 0.1 is negligible. Plus 0.1 to 0.3 is weak. Plus 0.3 to 0.7 is moderate. 0.7 to 1 is strong positive. These are the values you need to look for. The values and their meaning. So 0.7 to 1 is strong positive linear relationship. 0.3 to 0.7 is moderate. 0.1 to 0.3 is weak. 0 minus and negative is no relationship. And then you have strong negative, moderate negative, and weak negative linear relationship also. So correlation gives a value. Covariance simply gives you mathematical sign, whether it is negative or positive. This is to understand relationship between two numeric variables. Two numeric variables, if you want to understand the relationship, this is the. Now, in our data, bicycle data, double square bracket, CNT, comma, wind speed, both are numeric variables. Dot COV is covariance. So what is the mathematical sign you are seeing here? Negative. There is a negative relationship between bicycle count and wind speed. Opposite. They are doing in opposite directions. Right? We want, you can add one more variable. We have temp also, right? So between CNT and temp, it is positive. Between CNT and temp, it is positive. This value and this value are same. Okay. So between temp and CNT, it is positive. But wind speed and CNT, negative. No relationship between wind speed and CNT. There is a relationship between temp and CNT. Similarly, if you are looking at correlation, CORR. So between CNT and temp 0.62 and between CNT and wind speed negative. No relationship and relationship. 0.62 is somewhat closer to 0.7. Some sort of moderate relationship is there. There is a negative relationship between wind speed and CNT. See, this is the numerical terms. Correlation quantifies the relationship in numeric terms. Covariance, the mathematical sign, negative or positive. Okay. Similarly, the bivariate plot. The bivariate plot is called the scatter plot, which gives you the linear relationship between two variables. You can also use plot, the scatter plot. So you can see here different correlation plots of scatter plots. Okay. Now bicycle data, double square bracket, CNT, comma, 10. Oh, sorry. Bicycle data dot plot. X is equal to CNT, comma, Y is equal to 10, comma, kind is equal to scatter. Now you can see the scatter plot. Moderate. Moderate, right? This is your moderate correlation. Similarly, bicycle data dot plot X is equal to CNT, Y is equal to wind speed, comma, kind is equal to scatter plot. See, negative, no relationship at all. Spread in the horizontal. See, you can see like this, right? No correlation. This is the plot you can relate, right? No correlation. And then if you come down, you can see this also looks like no correlation. So the scatter plots will help us to understand whether there is a relationship between two variables is there or not. So covariance, correlation are the metrics. Scatter plot is the visualization. Relationship between two numeric variables. So for covariance is dot COV, CORR is for correlation. Okay, can you scroll down? Now, correlation and covariances are very important when you are using dimensionality reduction techniques. There we use covariance as the input or correlation as the input. Factor analysis. So in advanced clustering algorithms, we use them as input. The correlation matrix will be the input for typical PCA, principal component analysis, or a factor analysis. So there we use this covariance matrix and correlation matrix as input. Correlation is also important in regression.
we can find correlation between n number of it's
But the problem is you will be having problem in terms of understanding the output. So the best way of understanding the input output would be, say you are, can I scroll down? Say for example, we have numeric variables, right? Bicycle data, double square bracket, CNT, casual, registered, wind speed, 10, 810, right? All these things are there in numeric variables in our data. Anything else we have in numeric? Humidity is also there, huh? Humidity is also there, HUM. Comma, HUM, humidity. Dot CORR. See, you can get the matrix like here.
really lot it will be confusing.
So plot will be easy. Import Seaborn as SNS dot heat map. Comma not is equal to true. Now you can see the color scaling. Lightish white color is 1. And darker colors are lower values. You can see the color scale, right? Dark to light. So lights, so you have 9, this is light, right? 8M to temp, very strong relationship is there. Similarly, 9, 5, register to casual is there. So this is very helpful. When you have very large data, we use this heat map. N0 is equal to true will give you the values also. If you don't give N0 is equal to true, you will get only the color matrix without any values. Again, you need experience to understand this plot. By adding this N0 is equal to true, you are adding the values, the correlation values in the boxes. Yeah, it's data labeling. N0 is data labels. Annotations are data labels. So same thing, when you have large scale data, sometimes even this also we have difficulty. So what we will do is we will write the output into an Excel sheet. In Excel sheet, you have color scaling, right? So when you have large scale data, what we do is we'll write the correlation matrix into a Excel sheet. 2_Excel. You can write it pd.data frame, convert it into data frame, write it to an Excel sheet. In Excel sheet, you have color scales. In Excel sheet, we have conditional formatting, right? Color scales. Red, green, yellow, red. That means strong correlation will be green, medium will be yellow, lowest correlation will be red. So this also we have to do. Excel is compulsory. So in between, you have to move your outputs to Excel. When you get large scale outputs, you have to write it into Excel. And then we use conditional formatting like color scales. Sometimes you have 200 variables, or let us say you built a model with 110 variables. You can't analyze here. So you have to write the output into an Excel sheet. Then you sort the variable p-values. Based on the p-values, you will sort them, smallest to largest. Then you will start analyzing which are the significant variables. Like that you have to do. So Excel is mandatory. And sometimes the outputs are easy to sort in Excel compared to your R and Python. Now, over a period of time, once you gain comfort in Python and R, you will do the same things here also. I can do the sorting in Python also. Simply writing a simple for loop, I can subset the p-values and then I can write a loop to get the sort with the names. But for that, you have to write a loop, little bit of programming knowledge is required. If you don't want to do it, copy it into an Excel sheet, go to conditional formatting, color scaling, do it. And that sheet can be sent, you can easily, color scaling will tell you which is strong, which is medium, and which is weak. So that is how Excel and data science are very interrelated. In the latest version of Excel, you have a lot of functions Microsoft itself has added into data science related things. So you will have a lot of data science related things coming up in Excel in the next version also. So they are giving tough competition to Python and R. Okay, so correlation and covariance, which we call, they are for the relationship between two numeric variables. Two numeric variables. Okay, you can look at this. These are all the numeric variables we have. Seaborn is a sub-library of NumPy. It's a pure visualization library. Like Matplotlib, Seaborn is a library for visualizations.
So Matplotlib is completely Seaborn completely NumPy. But the
Matplotlib is also part of NumPy. Actually, no. Matplotlib is a separate library. It's not part of NumPy. In NumPy, you have Seaborn and Plotly. Two libraries are there. Seaborn is exclusively for visualizations. Matplotlib is used for adjusting the windows, plot. If you are creating your own plots, for that purpose, we use Matplotlib. There are a lot of other hypotheses. There are other hypotheses, we call them as non-parametric things. One of the popular non-parametric we don't use in business. They are more into academics. Yeah, Mann-Whitney test, signed Wilcoxon signed rank test, Kruskal-Wallis test. So these are their non-parametric t-test or what you call. These are made up based on medians. Again, these are completely different. They are more used in what you call academic studies, not in business studies. Business, we use those tests only. Scientists, these Mann-Whitneys, they are made purely based on medians. So what happens is, when you have very, very highly problematic numeric data, when you have very high skewness or kurtosis and your data, your variable is completely out of range, like what we call, in our case, the CNT is little bit out closer to normal distribution, right? See, this is normal, no outliers, nothing, the box is in the middle. Look at it, it's slightly towards the left, positive skewness, and some outliers are there. This is also you can use it for that. If the data is too much skewed, that means completely skewed with outliers, it's completely what we call what we call outliers, the data, you can't even get a box plot shape, then we can go for non-parametric tests. But that situation very rarely exists in business, because in businesses, what happens is we have certain amount of normality. We will have sales, right? We will have extraordinary sales, we have weak sales also. But that will have certain amount of range, right? They will be not out of bound. Suppose some stores might do sales in hundreds of crores. Some sales will be 50, do it in lakhs. Let's say 50 lakhs. That's all. Other than that, you won't have stores that do sales in thousands. You don't have say, stores doing sales in thousands of crores. That will not happen. When your data is like that, then it becomes a too much of a variance. When you have too much variance, I told you, median has to be taken into consideration. So these non-parametric tests all use medians. But in business, in hypothesis testing, we assume certain normality. Generally, businesses have certain amount of normality. If there is abnormality is there in business, that means your planning is wrong. We have a lot of planning and all, right? We plan, we forecast, we execute our plans. So we expect some normality in business, right? So that is the assumption we use, and then that is where the basic hypothesis testing we use. Everything is planned in business, right? Right from your purchasing of raw materials to selling of the goods, every stage is planned. Every stage has its own budget. Every stage has its own executions. So you will have slight deviations, not big deviations. So when you have such big deviations, then data will be completely skewed. But that scenario will not happen, right? Because businesses follow a plan. There is no business which does not have a plan, right? Every business has certain plans. Then plans will have stages. Each stage has its budgeted, targeted, overlooking, parameters, everything is there. So we assume normality in business, because business has to be normal if it is properly planned. If business is abnormal, that means there is problem in that particular business. Either it will go bankrupt or it will shut down. Satyam, you remember Satyam, abnormality of business. That's what happens. Vijay Mallya, Kingfisher Airlines. But if you have a normal, stable business, you will never go out of business. You will be staying in the business for longer period of time. So normality is one assumption we make in business. Every business has that normality, right? Infosys, TCS, their revenues on quarter to quarter will go up by 10% or 15%. Will their revenues jump by 100%? No, right? If they are jumping by 100% means there is some problem. They made a mistake in assuming or some problem they had created. So generally quarter to quarter growth happens by 10 to 12%. Year to year they grow by 10 to 15%. So there is some normality that we assume. Accordingly, they recruit employees, right? A normal strategy of recruiting employees. They don't recruit 1 lakh employees in 1 year, right? They have a proper methodology, method and all. So normality is assumed in business. So we use normal parametric hypothesis test in business. Got it? Everything is planned in business. That is the fundamental assumption. Everything has proper planning and all. So we don't see abnormal data. Abnormal data rarely happens, particularly in case of Amazon or Flipkart. That too happens for 3 days. That Great Indian sales or big sales, Black Friday sales, that's an exception. But that also will be normalized over a period of time. That is the only thing. Otherwise, everything is normal. Right? You can't outgrow very fast. So that is the normality here. So there are non-parametric tests that use median. In non-parametric tests, they use median. Because mean will be distorted, right? So mean will be distorted, and these non-parametric tests, the popular ones are this Kruskal-Wallis test, Mann-Whitney U-test, Wilcoxon signed rank test. These 4 are the popular tests, which are mostly used in academic studies, not in business. We use them in academic studies. Where? No. Chi-square is not related to what you call skewness and all, no? It's a cross tabulation. It's a classic non-numeric data, right? We are using frequency counts. Where? That is difference between, they are discussing this. Difference between parameter and non-parametric, they are discussing there. But these are the non-metric parametric tests. Okay. Same. Yes, each and every variable has to be analyzed through descriptive statistics. No. For hypothesis, see, once you've done the exploratory data analysis, you will know which are the important variables. For those variables only, you will conduct hypothesis test. The purpose of exploratory data analysis to identify critical variables and non-critical variables. You will conduct hypothesis test only on critical variables. On non-critical variables, you will not conduct the hypothesis test. Hypothesis testing? Yeah, that's what. If it is a critical variable, you have to include in the model, right? That's obvious. If it is a critical variable, you cannot ignore it.
And critical. Thing. Wait to reject now.
Uh, yeah, that also happens. So what happens is if you think it's a critical variable, but hypothesis test says fail to reject, still you will add that variable to model. And if the model also rejects it, you have to go with the thinking that it is not a critical variable. So if sometimes what happens is if the hypothesis says it's not a critical variable, but when you include it with other variables in the model, the other variables also affect, right? See, when you are looking at a model, when you look at a hypothesis test, you are looking at two variables. One variable affecting the other variable. But in model, you have a lot of variables affecting each other, right? There is an interaction between variables. When this interaction in the variables happen, there your the variable, the hypothesis test fails, the model will take into consideration. So simply, if the hypothesis test says it's failed to reject, you can't remove that variable. You still include it in the model. Look for the interaction with the other variables, because in model, all the variables interact with each other and also with the dependent variable. Then you will come to know the actual value.
But they will indicate in the last column is the dependent column and the all other columns.
Not like that. Not last column dependent is not like that. It will not happen in industry. Here it is, data is sorted, you got it. The column can be anywhere, it can be in the middle. You have to separate it as a dependent variable. Not every time last column will be dependent variable, first column will not be dependent. In real time, it doesn't happen. It can be column 23, it can be column 50, column 78 or anything. You have to separate it manually. And then you have to select those independent variables based on certain selection methods, and then you build a model. And you can't build a model with hundreds of variables. You have to compulsorily bring down to a lower level. So if the client says, no, I want only model with 20 variables or 30 variables, you have to use variable selection methods to even bring down them to 20, 30 variables also. So client will dump the data. The data will have hundreds and hundreds of columns. You have to clean, and then once you get a format, then you discuss, you ask him how many variables you want, then what type of model he wants. Accordingly, we agree, and then we build the model. So model building is just the last part of it.
So